So is my screen visible now?
Yes.
Okay, fine. So for those who have possibly missed previous class, so these are the people involved for your laboratory. So I'm Devashish Sarkar, and with me Professor Harikrishnan is there. Our email addresses are given. In case if you want, you can contact us. And we have three TAs, Gargi Jadhav, Arnab Dey, and Ishke Nishant. Okay, and this perhaps is important for you. Your assessment will be based on both your performance in laboratory, how well you prepare your laboratory manual. That will contain 60% weightage, and then at the end of all your experiments, we'll conduct written test and or viva. See, I say and or, right? So that will contain 40% weightage. And this is your laboratory schedule. So what is important here is we have scheduled the test for this on 6th of April. Okay. You will be complete your experiment by 30th March. Okay. So now I'll give you a very brief introduction to this batch distillation, studies on batch distillation, the experiment that we will perform today, virtually perform today. Is basically what we will be doing is we will verify the Rayleigh's equation related to this simple distillation, also known as differential distillation or Rayleigh's distillation sometimes. You have done this course, so you know you're familiar with actually batch distillation, familiar with continuous distillation. You perhaps know that batch distillation is commonly employed for small, when you have to handle small amount of material but which is high value or high purity is required. Like so, typical applications in the areas of biochemical products, biomedical products, or pharmaceutical products. Now, batch distillation can be carried out with reflux. Okay, pretty much similar to what you have done in continuous distillation. If you look at the rectifier section, is very much similar to that. So instead of the entire stripping section, you have a reboiler over there. So you can, let's just think of the simplest case of binary mixture. Okay, a more volatile compound, let us say A, and less volatile compound B. So when you start heating, and you know that in all distillation, what you do is you have to separate the phase. So for separating phase, you apply heat, so you generate a vapor phase. And both the vapor phase and the liquid phase will have all the constituents present in it. But the vapor phase will be, as you start heating, vapor phase will be richer, and vapor phase will be richer in the more volatile component. So if you condense the vapor phase, now you have two liquid phases. The liquid phase that comes out of the condensation of the created vapor phase upon heating will definitely have more concentration of more volatile components. So some sort of separation you have carried out. Okay. So here what you see is a batch distillation with reflux. Okay. So you can imagine that if you contain various portions of this overhead condensed product, right? The first cards will be very rich in more volatile component. Okay. And if you have say three components, multi-component mixture A, B, and C, the first cards, okay, that means the first portions of vapor that comes out and you condense will be quite rich in A, but definitely some amount of B and C will be there. Then the middle card will predominantly be B, but will also be associated with A and C, and so on and so forth, right? Now this you can also perform this batch distillation in a simple kettle like this. Okay, so which will, this do not have any reflux. See, that's the main difference. We will call this as a simple distillation. So what you have is basically a kettle where you take the, let us say I take the binary liquid mixture and I heat it, okay, and I heat it, and then the escaping vapor that if escaping vapor you condense, initially the vapor will be richer and richer in more volatile compound, but that concentration will go down. So for a period of time, if you accumulate the vapor, if you condense the escaping vapor and accumulate, so you will basically carry out some kind of separation, and that condensed vapor will be now richer in more volatile compound compared to whatever liquid mixture, binary liquid mixture you started with. So this actually can be done in a large kettle and doing this kind of distillation. But so laboratory replica of this, a small scale laboratory replica of this will be this. And this is what you will have in our laboratory, for which you will be given data today and you will be performing the calculations. So you have this round bottle flask where you take the, let us say, binary mixture. For your case, actually, you'll be taking acetone plus toluene mixture. So this binary mixture, you heat. So when you heat, the vapor that comes out will be richer in more volatile components. So if you cool it down using a condenser, the condenser that you receive here in a container will be rich in more volatile component A. Now we keep on heating. Let us say I heat so that at least 1/3 or 2/3 of this initial liquid is vaporized. Note that the concentration of this vapor that comes out will keep on decreasing in more volatile concentration A. Right? Initially it will be very rich, but it won't be so with time because the A is depleting from the steel, from this steel here, right? So the composition of the condensed vapor that you get will keep on varying with time. So over a period of time, you can find out the average composition in terms of A in this distillate. Okay, so and that will definitely be different from this in terms of A as well as B. So you have separated this mixture. Initially you have A and B here, you have taken out more here, A here. So this is basically simple distillation, also known as differential distillation or radial distillation. And the data that we will be giving you corresponds to this. Okay, this is exactly this we have in our laboratory. Okay, this is the condenser. Also note that the cooling water inlet is this side and cooling water outlet comes out from this. Okay, so you basically have a counter current flow for effective heat exchange and cooling. So before we understand this how this simple distillation works, or in other words, we derive the Rayleigh's equation. Just let me spend one slide for discussing this flash distillation, also known as equilibrium distillation or flash vaporization. See, flash vaporization or equilibrium distillation is a single stage operation. Okay, it's a single stage operation where what you do is you take the feed mixture. Okay, you take the feed mixture, then heat it up. Okay, reduce the pressure. Then what will happen is it will partially vaporize. So a liquid mixture is pumped through a heater and raise the temperature. Okay, so enthalpy is increased. It then passes through a valve where the pressure is reduced. So it will cause the liquid to partially vaporize. So you take this partially vaporized liquid and vapor in this flash drum. Okay, this liquid and vapor will approach equilibrium and you can take out the vapor, you can take out the liquid, and these two compositions will differ, right? So we have again carried out some kind of separation. Now, if you So this is important. The product and liquid vapor phases will approach equilibrium. Okay. Now, okay. So now, in case of this differential or simple distillation, we can just think that the fast flash vaporization just we just talked about, you are carrying out a very large number of such flash vaporizations. You are doing it successively of a liquid mixture, and each time you are vaporizing a very small amount of the liquid. So essentially you just consider that the flash vaporization is being carried out successively for a very large number of time, and each time you are taking an infinitesimal small amount of the liquid. Then the net result will actually approach the simple distillation that we have been talking about. So here you have taken out the binary mixture A and B. Initially you charge the still with the binary mixture A and B, and then you heat it up. So the vapor that comes out, you condense and collect the condensed vapor here. Now, when you heat it very slowly, we can imagine that the vapor that is generated is in equilibrium with this liquid. Okay. Remember that no reflux is there, no entrainment is allowed. Otherwise, this vapor in equilibrium with this liquid in the steel will not hold. So now, so the main assumption is this, that vapor that is coming out of a differential distillation will be at any given time in equilibrium with the liquid from which it rises. Okay. So now let us do then the differential mass balance. Note that the approach has to be differential mass balance. So you can write in terms of total mass balance. You can write also mass balance in terms of component A, which is more volatile. It's a batch process, so there is 0 moles in, 0 moles out. Sorry, 0 moles in for the total mass balance, 0 moles in for the component A balance, because whatever you have taken, it is initially, there is nothing coming in. Moles out. Okay, before that, I forgot to, okay, let us consider this on which we are writing down the mass balance equation. Let us consider that at any time during the distillation, there are L mole of the liquid in the still with composition X mole fraction of more volatile component A. So there are L moles of liquid in the still of composition X mole fraction A, and DD mole of distillate is vaporized of mole fraction Y star in equilibrium with the liquid. Okay. So L mole of liquid in the still of composition is X mole fraction A, and an amount of DD mole of distillate is vaporized of mole fraction Y star in equilibrium with the liquid. Then we can write this mass balance equation. So moles in is 0 for total material. For component A will also be 0, obviously. Moles out, so DD, right? DD amount of distillate is vaporized. So moles out, to, in terms of total mass, it is DD is out. And how much of component A is out? So that will be Y star into D. So Y star is the mole fraction of A in the vapor phase. That is in equilibrium with the liquid. That's why we put Y star. So the moles out, that is moles of moles A out, right? Y star into D. Moles accumulated, DL. Okay. And in terms of component A, this is small d, differential of L into X, which is LdX plus XdL. So now you write the mass balance equation as in minus out equal to accumulation. So in minus out equal to accumulation. So 0 minus dd equal to dl. Similarly, 0 minus y star d equal to ldx plus xdl. We can write this. So this, now we just concentrate on these and these. Okay. So you have dd here, which can be substituted in terms of dl using this relation, that dd equal to minus dl. So this will be, this minus that minus will be now positive. So y star dl will be equal to ldx plus xdl. That upon rearrangement actually will get the Rayleigh's equation. Okay. So now you can rearrange and integrate. So from the starting composition to the end composition, let us say we initially start with F moles of the binary mixture with composition except the feed mix. So that is the characterization of feed. You have F moles of the charge of composition except. So F moles, note that all these things are in terms of more volatile component A. W is moles of residue of composition XW. Okay. So now upon rearranging this equation, you can integrate from W to A and XW to XF. So you basically get this. So if you look at this equation, see this y star and x are related by the equilibrium relationship. So if you have talking about acetone and water binary mixture, so the equilibrium relation between acetone and water will give you this y star versus x, and that data can be used to find out this integral. This integration can be done both graphically as well as numerically. Now, if you look at this equation, which is known as Rayleigh's equation, so you can find out if W except XW when any three are known, right? We can find out any of these, any one of these, once three are known, because these four are related by this Rayleigh's equation. So you have to find out, or you have to what you have to do, you have to demonstrate that this Rayleigh's equation holds true for this acetone toluene mixture on the basis of the data that are being supplied. So you assume that you have done that experiment, you have collected these data, and now you are verifying that this Rayleigh's equation is valid. So you can perform the experiment, that integration graphically. Okay. You can also find out the integration numerically. So any numerical integration scheme can be used. Okay. What will be the average displaced composition that can be found out overall mass balance equation, right? So think of the overall mass balance equation. Total moles of A will be F into XF that you charge, right? Okay. And what left is, what is remaining is WXW, and what has gone as this distillate, which you are, that means this condensed vapor. Since the vapor has kept on changing its composition, you assume kind of average composition, YD average. So that multiplied by the distillate amount will give you the mass balance equation, overall mass balance equation in terms of A, and from this you can compute this YD average. Okay, so note that all other components are easily accessible, right? So you know what is the total amount of feed that you started with and its composition, what is the total, what is the residue that is left, okay, its composition can be found out, and you will be given this calibration which you will be using to find out these compositions, the amount of distillate that you have collected, that's a measurable quantity. Now since the composition kept on changing over the time, so this YD average composition can be easily computed using a simple mass balance equation like this. Any any concentration measuring instruments can also be used actually to measure the concentration of the collected and the condensed sample. Then you can also in fact verify whether this mass balance equation is valid or not. Okay, so that is all from my side. Now our TA will briefly tell you a little more about it. So if you have any question, you can ask. Otherwise, I'll leave it to TA now. Or if Professor Harikrishnan, if you want to add anything, or just let TA.
No, I mean, Devashish, I just wanted to say one thing, and not related to this one. I mean, regarding the, I mean, this is applicable to all, regarding the assignment submission. So we have extended it by 2 weeks, right?
No, that was only for the first one. That is only for the first one. Now it is next week only.
Even today, I mean, I have seen not a single assignment has been, among all the single has been submitted. So, this kind of things are becoming a joke. I don't think we will encourage it anymore.
No. It won't be encouraged anymore at all. Okay, number one. And I think that perhaps this MS Teams takes it up to 12 o'clock at night. So make sure that by 12 tonight, all the assignments are submitted. If the assignments are not submitted, TA will not evaluate. And that will fetch you 0.
True.
So please submit all assignments by due date. We have already relaxed enough that only one assignment per group. So you people can work as a group. You have been also asked to indicate indicate the contribution of each member. So it should not actually it should be done in this 3 hours time itself, right? Maybe another 3 hours time over the entire week you take. So please respect the due date. Beyond the due date, TA will simply not evaluate that. And each assignment will contain 100 marks. And out of that, 60% will be taken out. And the remaining 40%, Viva and or exams will be conducted, which will be individual. So myself and Professor Harikrishnan will individually take your Viva. We'll also take a written test. Okay, so but 60% weightage is there on this. So make sure that today before 12 midnight, you submit assignments. So if you at all want to get some marks for that. Okay, so anything else, Professor Harikrishnan?
No, that I think that's enough.
Right. Okay. Yes. So now, yeah, Arnab, you can you can start your presentation. Okay, I have unshared. Okay, yes.
Yes, then the screen visible, right?
Yes.
Okay. So this is basically the title of the experiment, the verification of Rayleigh's equation for batch distillation. So first of all, we will perform the batch distillation for a binary liquid mixture, acetone toluene mixture in our case, and then we will basically take the observation data from the given distillation to verify the Rayleigh's equation for the given mixture, that is toluene or acetone mixture. Okay. So this is basically the experimental setup available in our lab. In the left hand side, we can see the apparatus we use to perform the batch distillation. And in the right hand side, that is basically the refractometer we will use to measure the refractive index. So that refractive index is basically measured to determine the concentration of toluene and acetone in the mixture. Okay. So here is the basically the schematic diagram. So in the distillation flask, basically we pour the acetone toluene mixture and we allow it to distillate till a time, say 1/3 of the mixture is being distilled. So basically the mixture is vaporized, passes to the condenser and is being condensed and is collected in the distillate collector. So here we basically collect the distillate. Here is the procedure. So after that we have taken the distillate and the residue. We measure the refractive index of both the distillate and the residue. So this is to basically determine the mole fraction of acetone and toluene in the distillate as well as the residue. So after that, we will use those experimental values to determine to verify the Rayleigh's equation. So yeah, this is the calibration data for the toluene or acetone mixture. So in the left hand side, we can see the toluene concentration. That is, it is in percent volume. So it basically says the volume percent of toluene. So in 100 ml, how much toluene will be present? Say 20 ml first case in 40. So this is the case. So basically you have to plot this data with a refractive index on y-axis and the toluene concentration on x-axis, and we will use this data to determine the toluene concentration in distillate and residue. Okay, I will come to this later again. So this is the equilibrium data. So this is basically the vapor liquid equilibrium data. In the X basically represents the mole fraction of acetone in liquid phase, and Y represents the mole fraction of acetone in vapor phase. So acetone is basically the more volatile component over here. So we are representing it as X and Y. So these are the observation data, the densities and the feed conditions. So 400 ml of acetone and 200 ml of toluene as feed we will pour into the distillation flask, and we will allow it to distillate, say for the time till one third of it is being distilled, and then we will observe. Then we'll determine the refractive index of distillate and the refractive index of residue. So these are the observation data we have performed in the lab. So now coming to the calculation. Okay. So now we have provided you with the feed conditions. So that is 400 ml acetone and 200 ml toluene. So now since we know the feed conditions and also the densities I've also provided. So using these two things, you can easily determine the moles of feed and the mole fraction of more volatile component, that is acetone, that is XL. So now you have been provided the calibration data over here. This is the calibration data. So once you have obtained the plot, it will be a kind of straight line graph with a refractive index on y-axis and toluene concentration on x-axis. So here I have also provided, here we know the refractive index of distillate from the experiment. We have determined it using the refractometer. So now we can use that graph to determine the toluene concentration. So we will get the toluene concentration in percent volume, since the graph is basically the refractive index versus toluene concentration in percent volume. So now we can use that data and the densities provided to determine the mole fraction of acetone in the distillate. Now after that, similarly, we will determine the mole fraction of acetone in the residue, as we have the refractive index of residue as well. After that, these are the mole balance equation. F is equal to D plus W, and the component balance equation as provided. So F basically represents moles of feed, T is the moles in the distillate we have collected, the W is the moles of residue, and XF basically represents the mole fraction of more volatile component, that is acetone in the feed. YD is the mole fraction of more volatile component, that is acetone in distillate, and XW in the residue. So now once we have the F and W, W we have calculated using these two equations, mole balance equation and component balance equation. We can determine the LHS of the Rayleigh's equation, that is ln of F by W. So now coming to the RHS of Rayleigh's equation, that is the integration part. So here we have the equilibrium data. So once, so using that equilibrium data, what you can do, you can perform a plot of 1 by y minus x versus x. So once we have that, we can find the area of the graph from xf to xw. So that is basically the right hand side of the Rayleigh's equation. Or what we can do, one thing is we can fit it into a polynomial. We can fit this experimental data, equilibrium data, into a polynomial, say a 5th degree polynomial, and we can also integrate it from xf to xw. So these are the two ways you can find out the RHS of the Rayleigh's equation. So now once you have the left LHS and RHS of the Rayleigh's equation, you can compare them. Yeah. So that's it. If you have any doubts regarding the calculation or anything, you can ask. Also I provided you with the also I will provide you the okay. Also, this data I will upload in the MS Teams. So these are the calculation steps and the calibration data and equilibrium data. I will upload it in the MS Teams, and you can use those to perform the calculations and write your experiment.
Okay, fine. Okay. Yeah. So if anybody has any question, any doubt, can be raised now. Okay. So if not, then perhaps that's all from our side. Maybe now you can leave meeting and start working on it. What, Professor Krishnan? That should be okay, right? Okay then. Okay. Yeah. So we can leave meeting now and start working on it. So remember to submit your assignment number 1 today before 12 midnight. And every assignment should be now submitted by due date. And you will get 7 days time for each assignment now. Okay. Okay, I'll leave meeting then. Thank you.